Hi, welcome to Mathematics for Machine Learning. We have many times talked about linear regression, which is one of the most essential models in machine learning. We have looked at parameter estimation in linear regression by minimizing the squared error. We have looked at how you could penalize the weights as a way to regularize regression, to get rich regression. Today, we will reinterpret rich regression as a Bayesian model, and similarly to as we already did in the normal distribution, we'll find the posterior distribution over the weights for linear regression. Remember that in linear regression, we say that the data based on an input is used to predict an output. The link between input and output is the so-called model, and in this case it's a linear model. So we are saying that the relationship between our input-output pairs, so our x's and the corresponding y's, follows a linear relationship. So we say that yi, so each of those y's here, is a constant plus terms that are linear in the feature vectors that are contained in x, and that any deviation from this linear function would be considered random noise. So for a new x star, we would thus predict the corresponding y star by plugging this value, this feature vector, into our linear regression and make a linear prediction. Remember that in Bayesian inference, we would treat the parameters in a model as unknown random variables. Unknown random variables are also called latent variables. And we would learn a distribution of these parameters given the data. So this is different from making a single point estimate. So far for linear regression, we've always computed a single estimate of these parameters. For example, by minimizing the squared error over our training dataset. In Bayesian inference, the idea is that instead of providing a point estimate, we would compute a conditional distribution of the parameters given the dataset that we have observed. So the dataset that we're given won't be changed. It's a fixed quantity, so we condition on it. The part that is not fixed is the unknown parameters. The posterior distribution over these parameters, given this dataset, is then proportional to the likelihood times the prior distribution, where the prior distribution is everything that before we see any data we could use to say about our parameters. So in the prior distribution, we encode our assumptions and our desired properties of the parameters, including, for example, what could be a sensible value range for these parameters. And in the likelihood model, which is the conditional distribution of the data given these parameters that are plugged into our model, we define our assumptions about the data. For example, we could assume that the data is following a normal distribution. Now to do full posterior inference, to compute the posterior distribution, we multiply the likelihood with the prior, but this product is not itself normalized, so we have to divide by the marginal distribution of the data, the so-called normalizing constant. The problem with the normalizing constant is that it's often expensive to compute. However, there are cases where we don't need to explicitly compute this normalizing constant. And in the case of the Gaussian distribution, we already had such a case where if we placed the normal distribution as a prior over the mean, we could infer the posterior distribution over the mean, which again was a Gaussian. Today we will look at a similar case in order to derive the posterior distribution over the parameters of a linear regression. Before we start our model development, let's look at what we have done so far. In ridge regression, we have minimized the sum of a squared error and a regularizer to get our parameter estimate better, the ridge regression weights. We have, in order to do that, computed the basis functions in our feature vectors x. So remember, basis functions are potentially nonlinear functions in the original x that would make the resulting linear regression model nonlinear in the original feature vector. So while the linear regression would be linear in these basis functions, it could potentially be nonlinear in the original features x. So the prediction from the ridge regression is computed as phi of our training input vector x n times the regression weights, and the difference between the actual target variable yn and this predicted phi times beta is then computed, squared, and summed up over the whole training data set, giving us the sum of squares. The regularizer is the sum of the squares in the regression weights. Now, because we have the sum of squares, we can interpret these as actually Gaussian distributions. Because if we assume that our log likelihood over the data is normal, then we would get the minus the sum over the log normals over each data point. And in this case, the mean of this normal distribution would be our prediction from our model. And we would have a variance sigma squared. So we have independent normal distributions. They are not quite identical because each of them has a different phi of xn. So each yn is given its own xn to compute the regression. However, they are independent and all three parameters are identical. So the three parameters are the sigma squared and the regression weights beta. The normalizing constant of this log normal is sort of moved into an additive constant, such that we're just dealing with the part in the exponent to give us exactly what we have here. So if you take the log of the exponential function, you get exactly the yn minus the corresponding mean, which is phi of xn times the regression weights. And of course, we have 1/2 times this to the squared. Note that sigma squared here is also considered a multiplicative constant of the likelihood. So after taking the log, it becomes an additive constant. So all the terms that depend on sigma are moved here into the constant. At the same time, we also have the regularizer that can be interpreted as a prior distribution over our parameters. So similarly to computing with a log likelihood, we'd compute the log prior, because we have the sum of squares of the regression rates. We have here the sum over these IID prior distributions over the corresponding entries in the regression weight vector with a zero mean and a variance of 1 divided by lambda to give us exactly the term above in the exponent, where again multiplicative constants are moved into this additive constant here in this log posterior. So this is the log posterior distribution. In fact, it's actually a negative log posterior, which is then minimized. So this is equivalent to maximizing the positive log posterior. So regularized linear regression is equivalent to maximum a posteriori estimation in a model that has a Gaussian likelihood. So we're assuming that the residuals of the model are normal distributed with zero mean and variance sigma squared, and a prior distribution over the regression weights where we assume that each entry of the weight vector follows a zero mean normal distribution and has a variance of 1 divided by lambda, where lambda is the tuning parameter of ridge regression that adjusts the trade-off between the model fit, so minimizing the squared error for small values of lambda, and getting small beta coefficients for large values of lambda. In fact, not only ridge regression, so L2 panelization of the regression weights can be interpreted as maximum a posteriori estimation, but also other common regularizers can be interpreted in a similar way. For example, if you had the lasso, which is an L1 penalty on the regression weights, you could interpret this as using a Laplace distribution as the prior over the betas and doing maximum a posteriori estimation in that corresponding posterior distribution. But let's focus on the Gaussian, so the equivalent to ridge regression Bayesian model. The likelihood is the same as before. So we have, for a training data set of size n, the product over n independent normal distributions that all have the identical variance, but have different means, namely the mean that is given by the prediction for the corresponding input vector x and the one weight vector. And this normal distribution is evaluated at the y value for this training data point. We define a conjugate prior over the parameter vector beta. Beta appears in the mean. In fact, the mean of our normal distribution here, of the likelihood, is a linear function of beta. So similarly to the mean of a Gaussian distribution having a conjugate prior that is Gaussian, if we compute a linear function of beta here, then the conjugate prior is also Gaussian. So the conjugate prior is a multivariate Gaussian distribution. It has some mean vector that has the same size as beta. The mean vector is denoted by M0, and a covariance matrix that has squared as many entries as beta, that is denoted by S0. Remember that a conjugate prior for a particular likelihood, P of d given theta, is a prior that will have the same functional form as the posterior distribution. So we already know that the posterior distribution, P of beta, given our data, will be a Gaussian distribution because it has the same functional form as the prior distribution. So it will be a Gaussian distribution, of course, in our parameter vector beta that will have some mean vector and some covariance matrix. The goal of the lecture here will now be to find the posterior parameters M1 and S1. Let's look at this model in the form of a graphical plate model where every circle here denotes a random variable. Grayed random variables are observed. White random variables are hidden or not observed. The parameters in a Bayesian model are considered random variables that are hidden, so that they are not observed. And our data are considered observed random variables, so they are fixed, they are given, we can condition on them. Now we have n samples from this data set. So we have n pairs of inputs xn and outputs yn. And our model says that the yn distribution is depending on xn and this single parameter, well, by computing the linear regression model. So yn equals our phi of xn times beta, or not exactly, because we also assume that we have Gaussian noise. And this Gaussian noise follows a normal distribution at a zero mean and has a variance equal to the data variance sigma squared. So we have a single sigma squared that defines the variance of these residuals here. The posterior distribution is proportional to the likelihood times the prior. Let's instantiate this. So the probability of our betas given the data comes in y and x. Here we also assume that the value of sigma squared is known, so we can condition also on sigma squared. That is proportional to the likelihood. So the likelihood is independent for each data point with mean equal to the prediction from our linear regression. So that's phi of xn times the unknown beta coefficients with a variance of sigma squared times the prior distribution, which we said is a Gaussian distribution with mean m0 and variance s0. Alternatively to writing the product over n normal distributions, we can also say that the vector of all y values, so that's an n-dimensional vector, is following a multivariate normal distribution that has a mean vector that is given by the matrix of all the phi of x's, so that's the design matrix of our linear regression, times the same regression weights. So if we multiply this matrix of all the phi's, the design matrix times the betas, we will get a mean vector that has the same dimensions as y, so it's also element Rn, and a covariance matrix that is, well, because we had IID noise distributions, it means that all the variances are identical and that we have 0 covariances, so it's sigma squared times the n-dimensional identity matrix times our prior distribution as before. Now that is proportional to our posterior, which will have the same functional form as the prior. Because our prior is the conjugate prior over the mean of this normal likelihood. The parameters are as follows, which we can quickly derive by completing the squares. So if we look at the part in the exponent, we get for the likelihood minus 1 or 2 sigma squared y minus phi beta transpose y minus phi beta, where this is of course the vector of all y's, and this is the design matrix times the regression rates. And for the prior we get minus 1/2 times beta minus m0, the prior mean, transpose S0 inverse beta minus m0. Now we multiply out all of these terms, so we get minus 1/2 sigma squared times y transpose y plus 1 divided by sigma squared y transpose phi beta minus 1 over 2 sigma squared beta transpose phi transpose phi beta. Similarly, for the prior distribution we get minus 1/2 beta transpose S0 inverse beta plus m0 transpose S0 inverse beta minus 1/2 m0 transpose S0 inverse m0. Now we will group all of these terms by whether they are linear in beta the variable of interest, quadratic in beta the variable of interest, or whether beta the variable of interest doesn't appear at all, which means that we would move it into a constant. So, for example, here, this is a term where beta doesn't appear. Here we also have a term where beta doesn't appear. So this is equal to constant. Then we look at the terms that are quadratic in beta. We have this term here and this term here, minus 1/2 times beta transpose times 1 divided by sigma squared phi transpose phi plus S0 inverse times beta and the linear terms are plus 1 divided by sigma squared y transpose phi plus m transpose S0 inverse times beta. If we complete the square, it follows that this here must be the covariance matrix. So this here is S1 inverse. And that we can now use to complete the squares. Here we know that the linear term needs to have S1 inverse in there, so we actually need to multiply with the inverse of that, and the resulting vector here will be the posterior mean. So this will be equal to M1. And if we check this against what we have here, we see that is correct, just that we have it transposed here. So we have S1 times M0 times S0 inverse plus 1 divided by sigma squared phi transpose times y, giving us the parameters of our posterior distribution for a prior that is Gaussian with an arbitrary mean vector M0 and a full covariance matrix S0. Now if we look at the special case of that, which corresponds to our rich regression example, in that case M0 would just be 0 in our prior distribution, and S0, the prior covariance, would be just 1 divided by lambda times the identity matrix. So we have a 0 mean prior. All the regression weights are a priori to assume to be just as likely negative as positive, because we don't know much about their values, and they all should have the same variance of 1 divided by lambda, and they're independent of each other, so they have 0 covariances with each other a priori. In this case, M1 and S1 that we've just found simplify a bit. So M1 is just equal to S1 times 1 divided by sigma squared times phi of x transpose y. So the term that depends on M0 goes away because our prior mean is 0, and the posterior covariance S1 is given by the inverse of the prior covariance, so lambda times I, plus the term here that depends on the design matrix and the variance of the likelihood, so 1 divided by sigma squared, the variance of our data, times the phi of x transpose phi of x, so that's a scatter matrix of our feature vectors. So that's essentially summing up the inner products of phi of x n with itself over all our training data points. This sum is then being inversed. Now, for lambda equals 0, this will actually be equivalent to the maximum likelihood estimate, or at least the mean of this distribution will be equivalent to the maximum likelihood estimate. If we have a likelihood that is the product of independent likelihoods together with the corresponding conjugate prior distribution over the parameters of our model, Bayesian inference can be used for sequential learning, where the likelihood is combined with the original prior to compute a posterior, and which then can be used as a prior when we get a new independent data set to compute a new posterior distribution, which then in turn could again be used as a prior distribution in a next iteration. So as long as the data sets that we get are independent of each other, then sequential updates are possible and yield the exact same posterior distribution as a final result than if we had combined all of these independent data sets in a single step. Let's look at a simple example for sequential learning, sequential updates of a posterior distribution of a normal likelihood with a normal prior distribution over a linear regression model that has 2 weights. One weight that is multiplied by x and a second weight for the bias. So we have a likelihood for each training data point yn with mean equal to W0, the bias, plus our input value xn times W1. And we have a variance sigma squared, that's our likelihood. And we have a prior distribution as before over our weight vector, which is two-dimensional, W0, W1, with mean 0, and a covariance matrix that is given by 1 divided by lambda times the identity. Then, before we have observed any data, the prior distribution will have contour plots that look as follows. So the mode of this distribution, the point with the highest density, of course, is at the mean, which is the point 0, 0, and it is a distribution. So of course we can now draw samples from it, which will give us a pair of W0, the bias of a linear regression, and W1, the weight of our linear regression. And each of those samples will now correspond, of course, to a random function. For example, we could sample this function here, which is given for a pair of W0 and W1, or we could sample this function here, which is another pair of W0 and W1. Now these functions, of course, they don't mimic any data because we have not seen any data yet. So they're just arbitrary random functions that are given by sampling from our prior distribution. But now we observe a single data point, which has an x value and has a y value. And this allows us to combine a likelihood with the prior to compute a posterior distribution. So the likelihood, again, is parameterized by W0 and W1, and you see that it is highest along a diagonal line here and then tapers off. And the reason that it looks like that is that the pairs of W0, W1 that lie on this line here would be the ones that would create a function that would exactly pass through our point x, y. Whereas if we move away from this diagonal line, either in this direction or in this direction, we would produce lines that go further and further away from this point here. Now this likelihood is then combined with our prior distribution by computing the product over these two densities and renormalizing this product, which will yield a new normal distribution that now has a non-zero mean vector and has a negative covariance. To compute a posterior. In this plot, there is also a cross here, which is the true W0, W1 that perfectly describes the linear relationship for our training data. As we now sequentially receive more training data points, this posterior distribution will closer and closer go to this true value for W0, W1. So after we have observed 19 data points and we get our 20th, we see that the posterior combined again with such a likelihood will create a posterior that is very peaked. If we sample from this posterior distribution, we will now not get arbitrary functions, but only functions that are compatible with our 20 training data points that we have observed so far. So whereas in the beginning we produced functions that basically modeled arbitrary xy relationships, now they all have to be compatible with the xy relationship of the training data set that we have observed so far. Now, if we had a single fixed weight estimate, better had, then making a prediction with this model for a new unseen training data point where we get only the inputs x star would be trivial. We just compute the linear regression. So in this case, we say that we have a Gaussian likelihood model. We condition it on x star, plug in our weight estimate to compute the predictive likelihood distribution. So we would say that the mean is given by our linear regression prediction, which is phi of x star times our fixed weight estimate beta hat and our data variance. Now, because we have a Bayesian posterior distribution, not just a single parameter estimate, we actually are able to model the uncertainty in our parameters and actually bring these over to our predictive distribution. Of course, this beta hat might not be correct. It's just an estimate, which means there is actually some uncertainty in this estimate. Now, in Bayesian inference, we compute a posterior distribution. And the posterior distribution does tell us about the remaining uncertainty in our parameter estimates. In fact, here we have a Gaussian distribution, so the larger the variances of this Gaussian distribution, the larger our uncertainty. And the smaller the variance, the more certain we are in our estimates. Now, uncertainty in our estimates means that we are also uncertain in the predictions for new unseen data, because we essentially have to take into account that there is not just one plausible beta estimate, but a distribution of possible plausible estimates, which, if we looked at all of them, would give us actually a distribution of predictions of plausible y values for our new data point x star. It means that our predictive distribution here actually does not reflect this uncertainty. However, if we integrate beta over our posterior distribution, we take the uncertainty into account that is still present in our posterior. So the probability of y star given x star, its input, and our training data is given by the integral over b of p of y star given x star beta and sigma squared, so this is the same as above here, times the posterior distribution over beta and d beta. So we're taking the integral over beta. Now this posterior distribution, we said, is a multivariate normal distribution that has a posterior mean and a posterior covariance matrix. And if we compute this integral here, we get a new normal distribution in y star that has as a mean the posterior mean of beta times the input phi of x star. So that you can think of as our prediction. It's the mean of our prediction, but that prediction also has a variance, and that variance depends on the posterior variance as 1, but it's a squared form with phi of x star. And the resulting variance of our predictive distribution is the sum of this variance that comes from the posterior uncertainty and the data variance sigma squared. So that's the variance of the residuals that we would just get even if we had the perfect regression weight. The point is, the predictive distribution is again a normal distribution, but the predictive variance is increased because we take the posterior uncertainty in our parameter estimates into account. Now note, this is a feature, it's not a bug. So whenever we do parameter estimation, we actually also have uncertainty. We just don't keep track of it. So we just lose this uncertainty. So this shows a key advantage of Bayesian linear regression, because it allows you to compute the full posterior over the regression weights of a linear regression model and take this uncertainty of the posterior distribution into account when making predictions. And with this, I want to say thank you and see you next time. Bye-bye.